Now to something less general, but easier to use. So remember, the Cole's marriage theorem, it gives a necessary and sufficient criterion for the existence of a perfect matching or an X-complete matching. Now, necessary and sufficient is great, but the whole condition takes some, it's not always very easy to check. You might wish for a criterion that is maybe less general, maybe just sufficient, not necessary, but it's easier to check. And such a thing exists in the particular case of regular bipartite graphs. So what do I mean by regular? In a more restrictive setting, there is a simpler sufficient condition. The notion of a regular graph always comes with a k. It's called k regular, where k is a certain integer. So let k be a non-negative integer. A multigraph G is said to be k regular if all its vertices have degree k. So what are examples of regular graphs? Well, let's start with one regular. One regular graph is basically a graph whose edge set itself is a perfect matching. What do I mean by this? Why is this true? Well, how would a one regular graph work? Each vertex has degree 1. So if I have a vertex somewhere, it has to have only one neighbor, and that neighbor must also have only one neighbor. So these two vertices are adjoined to each other, but they're not connected to anything else. Then, if there is another vertex, again, it has only one neighbor, and that neighbor, again, the two form a self-contained system, and so on. So this graph is a disjoint union of graphs P2 of paths with only two vertices each, and of course, this is itself a perfect matching. So this is not a very interesting kind of graphs, but it's good that they fit into this definition as well. So in other words, one regular graph is a graph that is a disjoint union of copies of P2. What about a two regular graph? Well, we know from, I think, homework set 1 or maybe 2, how a connected two regular graph looks like. It is a cycle. In a cycle, each vertex has degree 2, so it's two regular. And we've proved that a connected two regular graph indeed has to be a cycle. But if it's not connected, then you can have another cycle. These two do not disturb each other. The degrees are 2 everywhere. And you can have as many cycles as you want. In particular, you can also have one cycle. So it's basically a self-loop. So a two regular graph is a graph that is a disjoint union of cycles. What about three regular graphs? Well, here all hell breaks loose. You can characterize one regular graphs, you can characterize two regular graphs, but there is no good way to characterize three regular graphs. All you can do is you can give them a new name. So the three regular graphs are known as cubic graphs or trivalent graphs. An example is the Peterson graph. We keep coming back to it for some reason. So just to remind you, here is how it looks like. It's a pentagon on the outside. I hope you can forgive my drawing skills. It's a pentagram on the inside. And the two are connected vertex by vertex like this. And as you see, each vertex has degree 3. So it's a three regular graph. And actually, any Kneser graph K as K is regular, but it's not K regular, it's regular for a different number. What number? Well, it's k element subsets of the set S, and adjacent means disjoint. So you have a k element subset. You're wondering how many other k element subsets are disjoint from it, and that number, as it's not hard to see, it is this here, because you have to pick k elements out of the remaining size S minus k elements of the set. Okay, so I haven't talked about regular graphs very much because honestly, there aren't that many things you can say about them. However, bipartite regular graphs are particularly nice. Here is a little, here is a simple fact you can show. So let gxy be a bipartite, or be a k-regular bipartite graph. Then so there is equally many left and right vertices. And in a way, this is sort of reasonable, because each left vertex has degree k, so it's connected to k right vertices, and each right vertex is connected to k left vertices. In a way, you would expect this to force it to be the two sides to be equal in size. So let's formalize this. Write G as G equals VE phi. Then the sum of the degrees of the left vertex is this number of edges, because each edge contains exactly one left vertex. This is very similar to the handshake lemma from long ago. You're double counting the number of edges. Each edge contributes to exactly one of those degrees, so the sum of those degrees is the number of edges. And of course, you can place this. Sorry, what have I said? Ah, yes, that's fine. So therefore, the number of edges is the sum of those degrees, but each degree is k because G is k regular. So you're summing a bunch of k's, and this is of course k times the number of left vertices. But the same argument shows that it's also k times the number of right vertices. So comparing this, we obtain that these two numbers are equal. And since k is positive, we can divide this by k and conclude this equals this. Okay, and to be very pedantic, it's not the bipartite graph, but the graph G that is k regular. So, but of course you understand what I mean. So it is a bipartite graph such that G is k regular. But now the maybe more surprising result, I call this the Frobenius matching theorem, because it's due to Frobenius. Everybody else just keeps calling it Hall's marriage theorem, except it's not actually Hall's marriage theorem, it's a consequence. So let k be positive, let g xy again be a k-regular bipartite graph. Then G has a perfect matching. Why is that? Well, I claim that each subset A of X satisfies the number of neighbors as at least the size of A. This is Hall's marriage. This is Hall's condition. To prove this, let A be a subset of X. Consider the edges of G that have at least one endpoint in A. Of course, at least one means exactly one because it's a bipartite graph. How many such edges are there? On the one hand, there are k times the size of A many such edges. Why? Because each vertex in A is contained in exactly k such edges. Remember, the graph is k-regular, so each vertex in A is contained in exactly k edges. And all of those edges will be counted because all of them have at least one endpoint in A. On the other hand, there are at most k times the size of n of A many such edges, because each vertex in n of A is contained in at most k such edges. Why? Well, each vertex in n of A is contained in k edges in total, and at most at most k of them have one endpoint in A. Is that you can also have an endpoint somewhere else. Okay, so comparing these two results, we obtain that the number k times the size A is at most k times the size of NA. And again, dividing this by k, we obtain this inequality because k is positive. And this is what we want. Okay, so this is Hall's condition. So since we proved this for every subset A of X, we conclude by Hall's marriage theorem that the graph G has an X complete matching. However, the previous proposition yields that the sizes of the number of left vertices is the number of right vertices. Thus, an X complete matching must also be Y complete. So think about this for a moment. It has to do with the fact that, of course, you cannot use the same vertex twice in a matching. If it's X complete, it has at least this many edges. So it has at least this many edges, and therefore each vertex in Y must be covered. Strictly speaking, if you look at this argument closely, it's a pigeonhole principle argument. So it's a pigeonhole principle. And I'll spell this out in the notes. And of course, if it's both X complete and Y complete, it's everything complete, so it's perfect. So G has a perfect matching, since we just showed that G has an X complete matching. And this proves the theorem. And this theorem has a particularly nice set of consequences, one of which we're going to see next.